Welcome back to this lecture series on deep learning. In this lecture, we will see some the basics about the loss functions and how it would be useful in machine learning and deep learning. We'll see one by one. First, we should know the understanding of the loss function. The loss function plays a central role in machine learning and deep learning because it measures how well a model is performing. In a mathematical optimization and decision theory, a loss function or cost function will be used. That will be seeing later what is the difference between cost function and loss function or error associated with a prediction. In simple term, it tells us how far the model's predicted value or from the actual value in the data set. A lower loss indicates better accuracy, while a higher loss shows that model needs an improvement. If you are getting the higher loss, we have to go for the further enhancement or the improvement. Since the loss function is mathematically defined based on the parameters of the algorithm, it guides the learning process by helping the model adjust its weight to reduce error and improve performance. That means accuracy. Basically, what is a loss function? A loss function is a mathematical tool that evaluates how far my model's predictions are from the actual values in the data set. It converts the prediction error into a single numerical error, that is predictions are from the, so what it will do is it converts the prediction error into a single numerical value that is known as the, that is called loss or cost, which tells me how well or poorly the model is performing. A lower loss means the model's predictions are close to the actual value. That means lower error means what? It will be closing to the actual value. While a higher loss indicates larger mistakes. Every machine learning and deep learning model depends on a loss function to understand its error and improve during training. Next, purpose of using loss function. The main purpose of loss function is to guide the learning process by showing the model how wrong its predictions are. It acts as a feedback mechanism that allows optimization algorithms such as gradient descent to update the model's parameters in the right direction. By comparing the predicted value output with the actual output, the loss function helps the model gradually adjust itself to achieve higher accuracy. Without loss function, the model would not know how to learn or improve. Next, the loss functions as a mapping. A loss function is mathematically maps actual value and the predicted value into a single real number that represents the cost of prediction error. This mapping can be written as loss of, so we can write it as loss of function of actual and the predicted, where no, and this representation sometimes we will be calling it as the cost functions. So higher cost means or worst prediction. The cost value tells the model how served its errors are. The mapping can be written as the loss, the function of yi, that means actual, comma yi gap, where yi is the real value and yi gap is the predicted value. The cost value tells the model how serves its error are. A higher cost indicates larger errors and a lower cost means the model is performing better, helping the learning algorithm to decide how much to adjust the parameters. Next, linear regression prediction. In simple linear regression, the model predicts output value using the linear equation y caps equal to mx plus b, where m represents the slope and b represents the intercept of the line. The slope determines how steeply the line increases or decreases. This is the basic equation what we have studied in the lower classes in the schools. while the intercept determines the lines crosses the vertical axis. These two parameters are adjusted during the training so that the predictor value closely match the actual value. If there is a match between this y cap and y, there is no it is equal, there is no error at all, but it should be nearing to the actual value. The loss function evaluates the accuracy of these predictions. Next, error for one sample. If you are taking error, yi minus y cap. If you are taking one sample, if you are taking for any single point, the basic error is calculated as the difference between the actual value yi and the predicted value yi cap. The error written as error yi minus yi cap represents how far of the model predictions is. A positive error means the model predicted too low, while a negative error means it predicted too high. This simple difference forms the foundation for more advanced loss calculations used to evaluate overall model performance. And if you are taking the squared error, to ensure that the positive and negative errors do not cancel each other out, the squared error is used. Yi minus y cap the square. Squaring the error makes all the value positive and penalizes larger mistakes more strongly than smaller ones. The squared form also provides a smooth mathematical surface, making optimization easier. Because of these advantages, the squared error is widely used in regression based loss function. Total loss is calculated with the MSE means mean squared error. I'll repeat once again, mean square error MSE. To measure model performance across all data points, we compute the mean squared error MSE, which is the average of all squared errors. Mathematically, mean square error is given by 1 by n. That means mean square means what? Mean means what? Average. So the total value squared error divided by n. How many n's we have taken? N into summation of yi minus yi gap this whole square, where n is the number of samples. Average means what? How many samples you are using? That will be divided by n. This single number presents the overall quality of the model's prediction. A smaller the mean square error. The smaller mean MSC means the model's predictions are close to the actual values, making it a standard and widely used loss function for regression predictions. Next, mean square error as a function of m and b, since the predicted value y cap depends on the slope and intercept through the equation yi cap is equal to mxi plus b, the mean square error can be rewritten as msc is equal to 1 by n yi minus, instead of this y we are going to yi minus y gap, yi we are going to substitute this value. So 1 by n. So here 1 by n summation of yi mxi plus b the whole square. This means that the loss is directly determined by the chosen value of m and b. There is no other parameters are involved. Therefore, the training linear regression becomes an optimization problem where we try to find the best m and b that minimizes this loss. Reducing mean square error brings the prediction line closer to the actual data. Next, loss function shape. This should be when visualized, the MSC loss forms a smooth bowl shaped, like bowl shape. It will be like a yeah, the model will be like a will be like a bowl shaped. So the MSE loss function forms a smooth bowl-shaped value known as a convex. This shape has a global minimum which corresponds to the best possible values of M and B for the model. Because there are no local minima, optimization algorithms like gradient descent can easily find the lowest point without getting stuck. This convex shape makes linear regression stable and efficient to train. Next, gradient descent updates. The gradient descent reduces the loss step by step by computing the gradients of the loss functions with respect to the model parameters m and b. So here, these gradient dou loss by dou m and dou loss by dou b. So we are going to differentiate. So the direction in which the loss increases. These parameters are then updated the opposite direction using the formula m is equal to m minus alpha into dou loss by dou n m, and b is equal to b minus alpha into dou loss by dou b, where alpha is the, what is this, all we know that this is the learning rate. Alpha is the learning rate. Alpha is the learning rate, and you know that the equation is given by b is equal to b minus alpha into dou loss by dou b, and repeating these updates gradually brings the model to a minimum loss. We have to keep on updating this value till we get the nearest actual value. So the importance of loss functions are, if the loss function is essential because it gives the model a measurable goal to minimize, enabling effective learning. It influences how the model updates its parameters, how fast it learns, and how accurate it becomes over time. Every machine learning and deep learning Every machine learning and deep learning algorithm relies on a well defined loss function to guide its training process. Without it, the model would have no way to measure error or improve. So, the compulsorily machine learning and deep learning should have the loss functions. So, coming into the comparison between loss function and the cost function. So, as far as the losses involved, these two we should know. The first row, if you are considering loss function and the cost function, the loss function measures the error for a single training. See here, it has been given. A single training example by comparing the model's predicted value with its actual value. So it tells us how wrong the model is for the particular instant. So in contrast, here the cost function represents the overall error of the entire model across the training. Here the single, this will calculate the overall error of the trainings data set. It aggregates all individual losses to show the total performance of the model. So the next, and if you are considering a role during training, here role during the loss function is used to during training. This it will be used to during training to compute the error for each sample, and enabling the model to understand how much it should adjust for that specific example. Whereas the cost function, however, is what the optimizer uses to guide the entire training process. This is very, very important point in this case. It minimizes the total cost so that the overall error across the data set reduces, and ensuring global learning rather than simple voice learning. Global, the entire model will be trained here. Next, the sample wise versus the data set. In this case, loss function works at the individual sample level, calculating how much error one particular input contributes. This allows precise evaluation of how each sample example affects learning. On the other hand, the cost function works at the dataset level, dataset combining all sample losses into one total value. This provides a big picture measures of how well the model is performing as a whole. And take for example, MSC, MAE, and binary cross entropy and binary cross, all of which directly measures the prediction errors. The cost function, however, here average or sum, it will be taking sum of all the individual loss values in the data set. Essentially, the cost function is derived from repeated application of the loss function across all data points. Next, if you are considering the model performance versus the parameter update, the loss function is mainly used to evaluate how well the model predicts on the per sample basis. It shows the exact deviation for each example. Whereas if you are taking the cost function, is used to optimize, used for optimization, because so also here it is determines the direction or magnitude of the parameter updates. So because how much in which direction or model parameter, that means weights or biases should change. This ensures that smooth and consistent learning across this entire data set. Next, flexibility, if you are considering, versus generalization. Flexibility versus generalization. Different loss functions are chosen depending on the task, regression, classification, or probability estimation, giving task specific flexibility. In contrast, task specific. In contrast, the cost is usually derived from the chosen loss function, but may also include extra components such as here we are using in the another case regularization. This we have seen it in the previous lectures to prevent what over this regularization mainly used to prevent the overfitting. That all we know that regularization is used to prevent the. This makes the cost function more suited for global and general optimization. So it helps understand per sample prediction in this case, and this will be used for total model predictions. So this is the comparison between loss function and cost function. All the learners should be able to understand what is loss function and what is cost function. Mainly, if you know all those differences, it will be easy to implement it. So coming into the if you are the coming into the summary here, in linear regression, the loss function measures how far the predicted value yi deviated from the actual value ya. And the squared error is used to avoid cancellation and to penalize large deviations more severely. The mean square error, the next point, the mean square error calculates the average squared error across all samples, and minimizing this value helps find the best slope and intercept. The entire learning process is driven by reducing loss, making the loss function the central component of model training. So that's all about the loss function. So whatever we have learned, this loss function will also plays a vital role in deep learning and machine learning for improvising the performances. Hope everyone understood about the concepts of the loss function, and also we have seen the various concepts, and finally we have seen the comparison between loss function and cost functions. So the remaining things we'll discuss in the next lecture. Thank you.